I'll talk a little bit today about the errors or the accuracy of our numerical solutions to differential equations. And so I wanted to just explain a little bit of terminology. In numerical calculations, right, we talk about approximation errors. That's the first bullet on this slide. And then we talk about rounding errors. That's the second bullet on this slide. So approximation errors are going to be our focus in today's class. Not so much rounding errors. That has a different meaning. So approximation errors are inaccuracies or imprecisions that arise because you are literally approximating something. We're going to use the Taylor expansion again. We're going to approximate a function with the Taylor expansion. When you make an approximation of the function with the Taylor expansion, you're ignoring terms in the Taylor expansion. And so that's an example of an approximation error. And we'll be talking in today's class about the order of the approximation error. So when we take these little steps, delta t, we'll be talking about errors at the level of delta t squared or delta t cubed or delta t to the power 4. So those are all approximation errors. Rounding errors are different. So rounding errors occur when you have a quantity like pi, or you have a quantity like a fraction, a half or a third, and you express it in a computer as a floating point number. So when you do that, there's some limited precision of the computer's expression of pi, a geometrical number, or the fractions 1/2 or 1/3. So that we would call a rounding error. The computer is rounding the value of pi or the value of 1/2 or the value of 1/3 to a certain number of digits. So that's a rounding error. Rounding errors are typically important. Rounding errors are typically troublesome when you have situations like the following one. Supposing you wanted the difference between two numbers that are very close to one another. Then when you take that difference between those two numbers that are very close to one another, the rounding errors in the individual numbers can cause big errors, much bigger errors in the difference number. So that's when rounding numbers are important. That's not so relevant for today's class. Okay. So we're going to talk about, as we work through a couple of new differential equations, we're going to talk about the Euler method, which is first order Runge Kutta method that we met in last class. And then we're going to talk about somewhat more sophisticated methods, second order Runge Kutta method, and fourth order Runge Kutta method. And we're going to look at the accuracies, compare the accuracies of these three different approaches to numerically solving differential equations. So we'll be looking at the approximation errors due to the three different approaches to solving numerically differential equations. So on this slide here, I'm sort of taking us back to the Euler method for solving say a first order differential equation. And in that method, if you remember, we make space discrete as a series of points rather than a sort of continuous time. And we step from one point in time to the next point in time, calculating the solution to our differential equation. So I'm kind of describing it here with this expression for the Taylor expansion, that we calculate the value of the function y as the dependent variable at time t plus delta t from its value at time t plus this first correction term in the Taylor expansion that's in proportion to the time interval delta t, and it involves the first order differential of the of that dependent variable. And when we do that, we're ignoring terms, contributions in the Taylor expansion that are t squared, delta t squared and higher. So I tried to picture that on these two little plots here. So the top one is where I'm just sort of imagining one step in which we're proceeding and calculating the solution to the differential equation numerically. And in the bottom one, I'm showing many steps. So our overall procedure in calculating the solution to the differential equation. So in each of the plots, I'm plotting time horizontally and the dependent variable vertically. In this upper plot, I'm just going from the initial time t to the subsequent time t plus delta t. The red curve on this plot, that's think of that as the true function, the true solution to the differential equation. And then the black line here on this plot, this represents in the Euler method, the estimate of the function at this next point in time. And you see they're different. The true function in my sketch is down here at this point. The estimated value of the function upstairs at this point here. They're different because of this approximation that I'm making. That I can approximate the difference between the function of y of t and y of t plus delta t is just due to this first term here in the Taylor expansion. And so I make an error, and that's what we call the single step error. And that error is of order the terms that are delta t squared and higher. So this is an error that we're making. This is our approximation error for a single step in the Euler method. Downstairs here, I'm imagining many steps in which I'm mapping out the function. And each of those individual steps has an approximation error. And those individual steps, approximation errors, will accumulate as I map out the entire function. And the overall error over the range of the function from, say, t0, the starting time, to some final time here after n steps, is that overall error goes as that time interval delta t rather than delta t squared. So that's again the approximation error in this Euler method. The single step error and the approximation error are telling you the sort of thing like, supposing you decided to improve my calculation, I'm going to make steps that are 10 times smaller. So that would be a way of improving your calculation. If you make your steps 10 times smaller, then the error on an individual step, that goes as delta t squared. So you're going to make that error 100 times smaller. But on the other hand, to map out your whole function, you've got to now make 10 times more steps, because you made your individual steps 10 times smaller. So the error as you map out the entire function is only going to be 10 times smaller, not 100 times smaller. It's 100 times smaller on an individual step, but you made 10 times more steps. So that's the approximation error in the Euler method for a single step and the entire steps to map out the function. Yeah.
So as you go down the terms, you see increasing order of delta t in the series of y equals delta t. So I mean, so because delta is like small, we like major contribution comes out from the first few terms, and is that why it's only like truncating down into only saying that single step error is delta t squared, not delta t squared in higher order terms?
Yeah, so that's a very good question. And actually so these other methods exactly address that. So in the Euler method, the dominant term, unless for some reason it was to vanish because of the particular function, the dominant term in the inaccuracy is from the delta t squared term. And the other terms, delta t cubed, delta t to the power 4, in general are going to be smaller. I mean, you could imagine a function where somehow that delta t squared, the second differential, was 0, right? And that term would go away. But for a general differential equation, it's delta t squared that's going to dominate. In the other methods, we're going to push that approximation, where the inaccuracy comes in, to higher and higher orders. And that's the reason for the other methods, to make the approximation smaller and smaller and smaller. I think it might become clearer on the next few slides. So related to your question, supposing you wanted to improve the accuracy of the Euler method, or maybe you would say, well, what I want to do to improve the accuracy of the Euler method, let's go back and think about that Taylor expansion. Right now, I'm only including that first correction, the delta t term that involves the first order differential. I would get a more accurate result if I include the next term, the delta t squared, that involves the second order differential. And if I wanted to get an even more accurate result, I could involve the next term after that. That's the delta t cubed term. And I would need the third order differential. So maybe the most obvious scheme for making the Euler method more accurate is to include further terms in the Taylor expansion. But that's typically not, you don't typically do that. And the reason you don't typically do that, it is the most obvious thing. The reason you don't typically do that is, in general, you don't know the second order differential of your dependent variable, the third order differential of your dependent variable, the fourth order differential of your dependent variable. So generally, I mean, sometimes you might know, but generally you don't know those differentials. You only know that first order differential that was specified by your ordinary differential equation. But the Runge Kutta methods actually get you to that higher order accuracy without having to calculate higher order differentials. So I want to show you how that works. So this is just to summarize them. As I mentioned, the Euler method is really a Runge Kutta method. It's first order Runge Kutta, meaning that the errors that occur in a single step are delta t squared. The second order, we'll talk about this, second order Runge Kutta. So second order there means that the errors in this method occur at delta t cubed. So it's accurate to delta t squared. And then the fourth order, and this is what's most commonly used, is that the errors in the fourth order Runge Kutta occur at delta t to the power 5. So it's accurate to delta t, this small parameter, to the power 4. So this is how the second order Runge Kutta method works. So again, I've showed you on this plot, I'm showing you on this plot, time horizontally, the dependent variable vertically. I'm showing you the initial point at time t, initial value for the function at time t, and I'm showing you us trying to estimate this second value of the dependent variable y at time t plus delta t. So what second order Runge Kutta adds to the Euler method is that it adds uses two estimates of the change in the function from t to t plus delta t, instead of just using one estimate. And it takes an average of those two estimates. So take a look at this first equation here. So this is the equation in second order Runge Kutta for the value of the function y, dependent variable at time plus delta time, in terms of its value at time t, plus the average, so this divide by 2 is just thinking of it as the average of two estimates of the change in the function between these 2 points at these 2 different times. And we're just calling them K1 and K2. So one estimate, K1, is just the Euler Method's estimate. You're just taking the derivative of the function at time t and multiplying it by delta t. So that's how we do it in the Euler method. The second method, look at this, is calculating the estimate of the change of the function from t to t plus delta t as the, again, here's the differential of the function times the time interval, delta t. But this differential of the function is estimated not at time t, the beginning of the time interval. It's estimated at the end of the time interval. So it's estimated at t plus delta t. And so you're kind of averaging these two estimates of the change, one obtained from the differential at the beginning of the time interval and one obtained from the differential at the end of the time interval. Now there's one little subtlety here. So when you get the estimate at the beginning of the time interval, you use the value of the function y at the beginning of the time interval to calculate its differential. And let's imagine we know that. What's the starting value? When you have to find the differential, the slope at the end of the time interval, you need the value y at the end of the time interval, but we don't know that. So all we can do is estimate it based on the slope at the beginning of the time interval. So here is an estimate of the value of y at the end of the time interval, from which we're going to calculate the differential. That's why, you see, I drew this slope for K1. I drew it evaluated at the point y of t. I drew this second one, this slope. I didn't draw it at this point because we don't know this point. We're trying to calculate this point. I drew it at where, based on this slope, you would think y would be at the end of the time interval. Anyway, the second order Runge Kutta estimates these, averages these two estimates, and by that gives an improved result. Now, I'm not proving it with the algebra here, but if you work out the algebra, what you can show is that this scheme is the one that cancels out the delta t squared inaccuracies. They cancel out, and you're just left with the delta t cubed and higher order inaccuracies. So by following this scheme of averaging these two estimates of the change of the function, you are now accurate to delta t squared in a single step rather than just delta t in a single step, which was the Euler method. Does that make some sense? Okay, so this is fourth order Runge Kutta, and I mentioned that often this is a compromise that's kind of used. It still has relatively simple formulas to calculate it, but also it's very accurate because it's accurate to delta t to the power 4. So in this method, well, let me just mention the sketch again first. So again, I've got time horizontally. I'm imagining a step from t to t plus delta t, and we want to know how the function changes from y of t at time t to its new value, y of t plus delta t at time t plus delta t. So we're trying to estimate that. In Runge Kutta 4, the change in the function from the initial time to the final time in this single step is a weighted average. I've got a mistake here, actually, I've just seen it. It's a weighted average of 4 estimates. It's actually K1 plus 2K2 plus 2K3 plus K4. So it's a weighted average of these 4 estimates of the change from the initial time to the final time. I'll update this in the notes. So there's a 2 in front of the K2, and there's a 2 in front of the K3. These 4 Ks, which are all estimates of the change in the function, one of them's obtained an estimate at the beginning of the time interval. So that was the one from the Euler method. Another one's an estimate from the end of the time interval that appeared in Runge Kutta 2 method. And then 2 more come from estimates at the middle of the time interval. And so if you look at these 4 estimates here, look at the time coordinates in the arguments of the differential. So y prime is the differential that we're going to multiply by delta t to get the change. In the K1 it's t, so it's at the beginning of the time interval. In K4, it's delta t, so it's the end of the time interval. In K2 and K3, it's at the midpoint of the time intervals. So we're sampling at additional points now inside the time interval, at the center of the time interval. So that's how we get an improved estimate for the change by greater sampling over this time range. You'll also notice this other point. So, well, we might know the value of the function at the beginning of the time interval, but we don't know, we can only estimate the value of the function at the midpoint or the end of the time interval. So the y arguments to the differential, well, this is at the beginning of the time interval. This is an estimate, and this also here is an estimate at the center of the time interval. That's why we take half K1, half K2. And this is an estimate at the end of the time interval. And so this is Runge Kutta 4, 4th order. And this combination, again, we're not going to do any of the algebra, because if you do the algebra, you wouldn't, by the end of it, well, you wouldn't be any more enlightened, I don't think. This algebra is the one that cancels out all the inaccuracies up to delta t to the power 4. So the inaccuracies come in a single step in at the 5th order. And so this is why we call this 4th order Runge Kutta. Does that make sense?
Any particular reason why we weigh K2 and K3 only, like 2 K2 and plus 2 K3 and K2?
Yeah, I mean, the real reason for that is it's this exact combination that cancels out everything up to delta t to the power 4. So if you just took the average, you wouldn't do that. But to see it is just a very complicated algebra. So, but that's the reason it is like that. Okay, so we're going to take those 3 methods and we're going to solve a differential equation with those 3 different methods, and we'll compare the accuracies. The differential equation I'm going to solve is 1st order differential equation. It's one I mentioned at the beginning of the class. It's the one that gives rise to exponential functions. So this happens when you have things that growth systems or decay systems. A common example of a decay would be radioactive decay, for example, or discharging a capacitor. Common example of a growth, for example, would be, it's first developed in finance for, investments. And if you got 10% interest on your money every year, that's, I can't remember who, it was Euler that worked it out. And I think it was in that sort of financial setting, this function was first discovered. So we're going to look at a first order ordinary differential equation. We're going to solve it numerically. It's going to be one for an exponential growth. And when we do it, all I did was take the code from last class that I used to solve a first order ordinary differential equation and just adapted it a little bit for this particular first order ordinary differential equation. And there's really just three main bits to that code from the last class. And it's still the same three main bits to the code in this class. There's one where we define our method for stepping from the function at one time to the next time. So in the last class, that was just the Euler method, where we just have this one term in calculating the new value of the function from the previous value of the function. In the code I'll show you today, I'm going to have this method, the Euler method, and I'm going to show you RK2, Runge Kutta 2, second order, and RK4, Runge Kutta fourth order. So we'll have three separate functions here to compare. In the last class, we defined a free-fall function to describe the differential equation. And I'm going to define a function here for my differential equation. This function is going to be the exponential growth function. And the exponential growth function just says that the rate of change of the function is equal to the value of the function times some parameter. So if it's like interest on your bank account, right, you get, which it was 10% a year, right? Whatever you've got in your bank account, at the end of the year, you'll get 10% more. So that's a growth function. So I'm going to define a function that describes that. And then the other bit of the code was just to define an array of times, and then just to walk through those array of times, stepping through those array of times, stepping through that independent variable, propagating the dependent variable, the function y. So that's what my code is going to look like. Okay, so I'll go to the code actually. Okay, so here's my code. Again, it would be impossible for me to type this out in here. We'd be here to Christmas. But I'm just going to walk us through it. So I just imported the math library here and plotting library here. And then in this little cell here, firstly, I'm defining some parameters that I'm going to use for the problem. So the first three we met in the last class, right? I'm going to take my continuous time and make it discrete time. And so I've got a number of time intervals. And because I'm going to be interested in the approximation errors, I'm going to make a relatively small number of time intervals so we can see the individual steps. I'm just going to make 10 time intervals. I'm going to make these steps 0.2 of a second in length, and I'm going to therefore cover a time range that is just 2 seconds. We've taken 2 seconds, we divide it into 10 intervals. Then I'm going to calculate this sort of numerically calculate a solution to a first order differential equation that describes exponential growth. So there's a couple of parameters for that. So one is the parameter lambda that describes the rate of growth. It's the growth constant. I'm just going to set that equal to 1 inverse second. And then there's an initial population. And I'm just going to set that equal to 1, that initial population equal to 1. And then we're going to start with that, and we're going to calculate a solution to the differential equation as a function of time with these 4 different methods. So let me set that up. In this next cell, I've got the 3 functions that we're going to use to calculate the value of the function at one time interval from the previous time interval. And I've also downstairs here got the function that's going to describe the first order ordinary differential equation. So this, upstairs here, this is the function I just cut and pasted from the last class. So this is the Euler method for calculating the value of the function y, say, at time t plus delta t from the value of the function y at time t. I've then written these two additional functions. So this is Runge Kutta 2, second order. If you remember, it's the average of two estimates of the change in the function. So you see that here. Here's the original value, y, of the function. Here's the next value of the function. And here I'm just averaging two estimates of it, K1 and K2. And K1 is the estimate based on the slope at the beginning of the time interval. So you see T here. And K2 is the estimate based on the slope evaluated at the end of the time interval. So you see T plus delta T here. And then we're just going to average those two. And we said that particular combination of estimates cancels out inaccuracies up to delta T squared. And the inaccuracies come in at delta T cubed. And then finally, I got this somewhat more complicated, but not really too complicated, Runge Kutta 4 method, so RK4. This is going to calculate, here I got the factors right. This is going to calculate the value of the function at the end of the time interval from the value of the function at the beginning of the time interval by taking a weighted average of 4 estimates, 1 at either end and 2 in the middle. And so here you see the weighted average. I'm dividing by 6 and I'm multiplying these 2 middle estimates by 2. And K1, K2, K3, K4 are given by those equations I mentioned here. And importantly, you see 1 is evaluated at the beginning of the time interval, K1. 1's evaluated at the end of the time interval, K4. And the other 2 in the center here are evaluated at the midpoint. And then we take the weighted average of those. So those are my 3 methods that I'm going to compare. And then finally, in the last class we had, for our first order differential equation, we had an equation for free fall, that the rate of change of the velocity is just minus g, is equal to a constant. In this case, for the growth equation, the rate of change of the quantity is in proportion to the quantity itself. So that's a growth equation. And the coefficient of proportionality is this growth constant. And I'm calling that lambda. So here you see the differential equation. Here's the rate of change of the function. Here's the function itself. And here's this constant, this parameter of the differential equation. Everybody okay with that? Basically the algorithms from the last few slides. Okay, so now at this point, we're really going to go ahead in exactly the same way that we solved the differential equations from last week's class. I'm going to make my array of times. So this is always a handy thing for this, linspace in NumPy library. It makes an array starting at 0, that's the first parameter, ending at TF, that's the second parameter, with n in intervals here. So that's my time array, that's my independent variable. And then actually I'm going to construct 3 more arrays, the function y, evaluated by these 3 different methods. So I'm kind of initializing them here to be arrays of n elements filled with zeros to begin with. And I'm calling them YE for Y calculated by the Euler method, YRK2 for the RK2 method, YRK4 for the RK4 method, obviously. And I'm going to initialize, I'm going to set their initial values So when we solve it, explicitly solve our first order differential equation, we need an initial condition. If you had a second order differential equation, you need two initial conditions, so on and so forth. So my initial condition is that the value of y at the first time interval is y naught. That was the initial population, and we set that to be 1. Okay. So now I'm ready to actually do the calculation. I'm just going to loop with a for loop through the time intervals, calculating the population at time I plus 1 from the population at time I by calling the Euler function, if I want to use that method. That's the first for loop here, or the RK2 or the RK4 functions if I want to use those methods. That's the second for loop and the third for loop. I'm going to compare it with the analytical solution. So this is a case, obviously, where we can analytically solve that first order differential equation by separating the variables. We got dy dt equals lambda y. We can rearrange it to dy over y equals lambda t, integrate the left and right hand sides. We get a solution which is an exponential function. It's this function here. So y equals e to some, missed out the initial population. I think I called it y naught, didn't I? Y naught times the exponential function e to the lambda t. So I'm going to do that calculation, and then I'm going to plot the results. So I'm going to plot t versus y for the Euler method. That's going to be in blue. I'm going to plot it t versus y for the second order Runge Kutta. That's going to be in green. The t versus y for the Runge Kutta 4 method in magenta, and I'm going to compare it all to the analytical result. And so that's what I got here. So let's take a look at this plot. Time is horizontally. Remember, we said we're going to walk from 0 to 2 seconds. So that's what I've got here. And vertically, I've got the population as a function of time. And the initial population was 1, if you remember it, time 0. On the curve, I've got this red line, which is the analytical solution. And then I got 3 sets of points. So you see here, I got the Euler method is the blue points. And I got green is the Runge Kutta second order method. They're kind of buried. I think you can just see the tips of them underneath the magenta points. And then I got the magenta points, the Runge Kutta 4. And what you see clearly is that the Euler method, in this case, with these fairly big steps, right, is not that accurate. That ignoring delta t squared in single steps and incurring in this time interval an error of order delta t, it's quite a big error if you just take 10 steps. So that's pretty inaccurate. And it's inaccurate because it's kind of assuming that, going from initial time to final time in each step, there's just a linear change in the function. But the function is growing exponential, so the linear change is not very accurate. If we do Runge Kutta 2, right, that's much more inaccurate. So that's accurate still, even with these big steps. It's pretty accurate because the errors are incurred for single steps at level of delta t to the power 3. But actually, you do see that it is gradually, you see the green points look like they're falling below the red line. They are gradually getting inaccurate, maybe by the level of 1%. This is obviously, the blue one's obviously inaccurate by 10% or more. The green one is sort of level percent. Runge Kutta 4, that's accurate to delta t to the power 4 on a single step. It's accurate to delta t to the power 3 on a time range. And you see on this scale here, at least, that the RK4 points are falling right on top of the analytical solution, even with these big steps. So despite the fact we took big steps, which you wouldn't normally do, I mean, if you wanted to numerically solve this differential equation, you wouldn't want to take big steps. The RK4 method is still really very accurate. If I took 100, supposing I took 100 steps instead, and we rerun this. Oh, I didn't mean to do that. I want to take 100 steps rather than 10 steps, but make them 10 times smaller. So I'm going to go over the time range. I wanted to go over the same time range, but in small steps, 100 steps rather than big steps, 10 steps. And so if we go down here, now look, the blue points aren't perfectly accurate, but they're much closer now because, because we shrunk delta t by a factor of 10, and the error for evaluating y over this range goes as delta t for the Euler method. We should now be 10 times more accurate. We probably were 10 times more accurate here. RK2 and RK4, which were already at least the percent level or sub-percent level accurate with 10 steps, are now way more accurate. They're on top of one another and top of the function with 100 steps.